All right, so we're going to look at a problem that says you are getting ready for a birthday party and sliding a bookcase, which has a mass of 100 kilograms, across the floor. The coefficient of kinetic friction is 0.5 and the coefficient of static friction is 0.63. What is the force necessary to accelerate the bookcase at a rate of 2 meters per second across your carpet? All right, so we are looking at sort of forces in motion together. It's a very basic problem of forces in motion. So lots of different types of problems with forces in motion. So we're interested in the force necessary, which tells us that we want to do a type of force analysis. So what object are we looking at, interested in examining the forces on, and the object that's then accelerating? Well, we're examining the forces on the bookcase. So our object is the bookcase. All right, so if we were to draw a picture of the bookcase, there it is, sliding across the floor, and that's a rough surface because we know that there's friction involved. Let's look at the forces acting on the bookcase. Just keep in mind that the mass of the bookcase is 100 or 1,000. 100 kilograms. All right, what forces, if I'm interested in the force, I'm going to do a free body diagram. What forces are acting on the bookcase? As it's being accelerated, we now know it's being accelerated because I want to know what the force is necessary to accelerate it. So it's being accelerated. Therefore it's moving. What are the forces acting on it? Well, we know there's the force of gravity because that sort of acts on everything. So we have our bookcase, our object of interest, and the earth, and that's acting in the downward direction. All right, well, you're pushing on it, so we have the force of the push. That's between the bookcase and the pusher. And I said it's accelerating in the positive direction. Now we're thinking about, we're getting it moving, and now we're moving it. It's moving in the positive direction, accelerating in the positive direction. That force is going to also be in the direction of its acceleration. So we have a force of the push. We don't know what it is. In fact, that's what we're interested in. We have the force of the push. All right, well, the bookcase is sitting on the floor, so we do have the force of the floor, which is a normal force in this case. It's just there because it's interacting with the bookcase resting on it. And that's between the bookcase and the floor. And that points in the upward direction. So there's our normal force. And finally, we have the friction. And we know friction opposes the motion. That's between the bookcase and the floor. What type of friction is it? Both are given. So how do I know which one to use? Well, the bookcase is already accelerating. We want to know what force it takes to accelerate it at 2 meters per second. So while it's accelerating, while it's moving, the frictional force that we care about while something is moving is the kinetic friction. And just keep kind of in mind that this is mu sub k times the normal force that interacts with the bookcase with the same surface. So sometimes there's two normal forces. We want the one with the same surface. In this case, it's the only normal force in this situation. And that opposes the motion. So there's our kinetic friction. All right, so if we examine each of those individual forces, we're going to number them and look at their components. And we can see this is a pretty straightforward one, looking at both the horizontal and vertical components. All right, force number 1, no horizontal component. The vertical component is equal to the force of gravity in the negative direction. Force number 2, well, that's the force of my push, and it doesn't have any vertical component. Force number 3, well, there's no horizontal component, but we do have a positive vertical component. And force number 4, well, it's the kinetic frictional force, and it's pointing to the left. but we have no vertical component. Okay, so our next step of the process, we want to know what force is required to push. We're interested in this force. So I'm going to sum the forces in the horizontal direction. Force of the push minus the kinetic friction force. Now, sum of the forces in any direction is equal to the mass times the acceleration in that direction. So I bring that down. Sum of these two forces has to equal the mass times the acceleration in the horizontal direction. All right, well, I'm interested in the force of the push, so I'm going to solve for the force of the push. That's equal to the mass times the acceleration horizontally plus the force of kinetic friction. Well, I know the mass, that's 100. I know the acceleration, that's given as 2, but I don't know the frictional force. I'm given the coefficients of friction. That's not the frictional force. Remember, the frictional force is equal to the coefficient of its respective type, in this case kinetic, times the normal force. I need the normal force. The normal force is related to the vertical direction in this example. So let's sum the forces in the vertical direction. They too equal the mass times the acceleration vertical, but we know there is no change in motion vertically, so that's equal to 0. So adding these up, I get the normal force minus mg is equal to 0. So my normal force is equal to mg. Now I could solve it. I could solve for mg and get a number, but let's just work with how that's related to our frictional force. So if I take this and plug it up here, then I know that my kinetic frictional force is equal to mu sub k times mg. And I can use that down here. So I end up with my force of the push is equal to mass times the acceleration that I'm experiencing or wanting to experience, plus my coefficient times mass times gravity. And now I can plug all my numbers in. I have them all. So the force of the push is equal to the mass of 100 times 2 plus my kinetic friction, which is 0.5, times 100 times 9.8. So I get 200 plus 9,800 divided by 2, 4900, and the force of the push is 5,100 newtons. So it takes 5,100 newtons to accelerate this bookcase along the floor. All right, good job.